Okay, hopefully this is working as a microphone. We'll find out later. So, yesterday we looked through domain and range. Pretty much just domain and range. We did talk about degree, and that's as far as we got. I want to point your attention back to the very first page of this lesson, which had down in the bottom half there a whole bunch of terminology that goes with graphs. Now, in a perfect ideal world, you would have all have taken applied 30th, and you'd have heard of all of this before. This is not a perfect world. People get assessed into here because your math level's good and we think you can pick it up. So you may not have heard of all these things before. So I'm going to run through them, and then we're actually going to do the first assignment together so that we can kind of get a handle on what's going on here. Okay. So I'm not going to go in order. I'm going to start here. Okay, so domain of a function is the list of all possible input values. It's a very simple definition. It's a harder concept to use in practice. Range is a list of all possible output values for a function. Okay, and degree we've looked at, right? In a polynomial function, the degree is the exponent, the highest exponent on an x that you see anywhere in there. Okay, so we've looked at those. So now, they're going to ask you about these other things, so when I say they, I mean me first. So I'll give you a graph, or I'll give you an equation that you can graph on the graphing calculator, and I'm going to say, state or tell me all this stuff about that graph. Okay, so I'm going to run down the list quickly. If you don't 100% get what I'm talking about, it'll make more sense when we do an example. Okay? The y-intercept is the point where the function crosses the y-axis. The y-axis is this one, right? So where that graph crosses that axis is the y-intercept. If it's a function, and I'm not going to go on a half-an-hour digression why, if it's a function, it will only ever cross the y-axis once. Okay? If it's a polynomial function, it will cross once for sure, guaranteed. Okay? X-intercept or x-intercepts are the points where the graph of the function, this really should say where the graph of the function, if I'm being anal retentive. Okay, you don't need to add that in, but the x-intercept or x-intercepts are where the graph of the function crosses the x-axis, the horizontal axis, right? There might be none, there might be one. For polynomial functions up to cubics, what we're going to look at, you could have up to 3 x-intercepts. Okay, you won't have more. When we get to sinusoidals, you could have an infinite number of x-intercepts, and we need to look at how that works once we get there. Okay. The maximum value is the highest y value reached by a function, and I'm underlining that for a reason that it becomes important when we'll talk about it. And the minimum is the lowest y value reached by a function. Now, we've talked about that a little bit before. When we were talking about range, we talked about how low does it go and how high does it go. Maximum and minimum are referring to that same thing. There's a little glitch in there. Okay. The turning point is any point where the function changes from increasing to decreasing or vice versa. That's way better with a picture. Okay, so just hold off on there and we'll take a look. So a line, for example, actually doesn't have any turning points. Okay, so we'll see what that looks like. And then end behavior is stating what quadrant the graph originates in and what quadrant the graph terminates in. If you don't know that word quadrant,
that one, like, kind of put up the 4 and see which one corresponds to, like, a T1 or T2.
Absolutely, you're exactly right. Okay. So, and again, I'll get into that with a picture. So I don't like this. Remember, we skipped this? Because if I just on day one said to you, blah, 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 we read all that out, it doesn't make any sense out of context unless you've seen this before. What we're going to do, what I'm going to do, you can do whatever you want, okay, is I'm going to flip to page 5. And you've got a question here. You've got an assignment. Normally the assignments in this book will be for you to do. And again, these aren't marked. These are the ones with the answers in the back, right? So you'll do them as practice to get ready for a hand-in assignment or then the test at the end of the unit, okay? I'm going to do this one with you together because we haven't had practice on this stuff. Okay, we have had practice on domain and range, which is down here. But that's it. Okay, so we're going to do this one together. So here we go. It says use the function terminology in the previous complete the following table. I don't know what happened there. I think it's supposed to say section and then 2. Complete the table. That's what they want you to do. Fill this out. Okay? So let's go down here. 3 graphs. All 3 graphs are polynomial graphs. How do I know that? This one's a line. That's a dead giveaway. This one's a parabola. Okay? And this one's kind of parabole, but it's got like a wonky woody woo in the center there. That is the technical math name for it. Okay? So let's go and see if we can fill this stuff in a little bit. A linear function, and there's a specific example up here, and we're going to fill in specific things, but for degree anyway, this is true for all of these functions, no matter what the graph looks like. What is the degree of this function if we could see the equation? 1. Right? The equation of this graph, if you care, is y equals x plus 4. Okay? Here it comes. Thank you. That's all I need is the... Can't see it. Y equals x plus 4. Okay, so highest exponent on the x is 1. That is a generality. If it's a straight line, the degree is 1, except for that dumb horizontal constant function. I am never going to ask you about a constant function on an assignment or a test. They might on the exam, so I'll remind you as we're doing exam review. Just watch out for this one little glitch. Okay? Vertical lines are not functions, and they will not ask about them on the test, on the exam, or in my test or anything. Right? Because the unit is functions. We can't ask about non-functions in a unit called functions. Right? So every other line is slanty. Might be slanty upwards, slanty downwards. Okay? Any line like that has a degree of 1. So if I ask you for the degree, that's all you got to write. 1. Okay? There's no unit with that, it's just a number. Okay? For a quadratic, degree 2. Okay? What's that? Oh, okay. In this equation, I don't know what the what the simplified version of this equation looks like without sitting here for a minute and going, I'm not going to put you through that, but it might look something like this. Right? So the highest exponent on any x there is a 2. If you have a polynomial function, the highest exponent is 2, you will get a parabola when you graph it. Okay? And then for a cubic, 3. Could look like this. Right? It doesn't matter what the other exponents are, or even if they're there, it's the highest exponent in the thing. Again, this equation does not match this graph. Okay? It's just, I'm just putting a sample up there. Okay, number of turning points. Yes. Okay. So let's start with the line, right? This doesn't turn. If this was a road and you were driving on it in your car, you would do this. If you did anything else, you would drive off the road. Correct? There are no turning points in a straight line. Okay? I want to talk about the difference. They talked about on the first page, they said the turning point is where the graph goes from increasing to decreasing or decreasing to increasing. Okay? I want to talk about what a decreasing and an increasing graph looks like. When you're looking at a graph, I don't care if it's linear, quadratic, cubic, or anything else, when you're reading a graph, you read it like you read the English language, from left to right. So if I'm looking at this linear equation, I would start here as left as I can see, and if I'm looking at it, I would look from here to here. And I would ask myself, as I'm traveling on this graph, am I increasing or decreasing? And when they say increasing or decreasing, they're referring to the y value. As I'm traveling from the left to the right, am I going up or am I going down? So this one, as I travel left to right, I'm going up. So this is an increasing linear function. Okay? I know if you go the other way, if you start up here and you go back, you're going down. But you're not supposed to read it that way. Left to right, always. And I don't care what country you're from, what country you're going to move to. It doesn't matter. If you go take math class and you do this stuff, they're going to say, read the graph from left to right. Always. That is a standard in math. Okay? So now look at this parabola. If I start on the left and I start traveling to the right but following the line of the graph, am I increasing or decreasing? I'm decreasing right now. I'm going down, right, until I get to here. There is an infinitely small point right there where I'm neither increasing or decreasing. I'm going sideways, for lack of a better word. And then I am increasing from that point. The graph just went from decreasing to increasing. That is a turning point. Okay, so how many turning points here? One. Look at that cubic. Starting on the left, what's happening right now? I'm decreasing, and now I am increasing. So there's one turning point. And I'm increasing until I get to here, and now I'm decreasing, so I have two turning points. Okay? I can write this down if you want, but I think you'll be fine just seeing it. All linear functions have no turning points. Okay? Straight lines. They don't turn. Okay? All parabolas have one turning point. Okay? Not all cubic functions have two turning points. They have a maximum of two turning points. I'm going to show you a cubic function that has 0 turning points. Okay? Is that a straight line? No. Is that a parabola? So by elimination, that has to be a cubic. Okay? It is. Just trust me for now, and we'll get more into how later on. Okay? How many turning points does this have? Okay? And you got to be careful, because I used the car analogy for the straight line. If this was a road, you'd have to, like, move your wheel and turn. But these aren't considered turning points, these little things here, because we're not going from increasing to decreasing. I'm increasing. My increasing slows down a little bit right here, and then speeds back up again. It's still increasing. It's increasing right through the whole graph. So how many turning points does this one have? 0. Okay? So for linear, always 0. For quadratic, always 1. And for cubic, 0 or 2 are your choices. Trust me on this for right now, a cubic will not have one turning point. And I'm going to, when we get down to end behavior, I'm going to talk more about that. Okay, and sort of how do we know. Okay. Okay, is everybody kind of with me, following along okay? Okay. You know to stop me, right? If I'm not making any sense, you're going to...
I'm sorry, you to like the value of y intercept, are you talking about where it falls on the graph, or how many times it crosses through the line?
where it falls on the graph. Okay? And that is a good question. They don't do this so much in applied, but they do this a lot in pre-cal. So in pre-cal, they might say, state the number of x-intercepts or y-intercepts, and then you tell me how many times it crosses, and then value of is where does it actually happen. Okay? So value of y-intercept, I want to know where does this graph cross the y-axis. Yeah. Yes. It's a quadratic function is the fancy name for it, but a quadratic function when you graph it will look like a parabola. Yes. But like if you're a math person and you see this, okay, the graph of that would be a parabola. But when you see this, you don't say that's a parabola. You say that's a quadratic function. And then the shape of the graph is parabolic. Okay? I don't care. If you point at that and say to me that's a parabola, I'm going to go, good work. Okay? Okay, so where does this straight line cross the y-axis? At 4. So the value of the y-intercept is 4. Okay, now you could say the point 0, 4 is where it crosses the x, y coordinates. Typically, when they want just the value, they want just the y value. Okay, it's not wrong. If you said 0, 4, nobody's ever going to mark you wrong. That's correct. Okay, but you only need the actual y value at that point. Okay. Does this graph have a y-intercept? Yep. Where is it? Right? There is where it crosses the y-axis at 0 on the y-axis. Okay. And then this one? Negative. Careful. Negative 3. Okay. Because I know they're hard to see, but you see how this line is a little thicker? Right? That's trying to show you that's the axis. Right? So negative 3. Okay, so here's a question for you. I said it already. How do I know that every single polynomial function will have a y-intercept? Okay, it's not a trick question, but how do I know? I said earlier today, I said every single polynomial function, which is what we're looking at here, whether it's linear, quadratic, cubic, quartic, quintic, and all the other x, right? Any polynomial function will have exactly one y-intercept, guaranteed. How do I know that without looking at them all? They can't go vertical, or they're not functions anymore. Okay? And I'm going to go back to domain. For all the polynomial functions, what was my domain? Do you remember from yesterday? Any x value, meaning it goes all the way left and all the way right. Well, if you have a graph that's going all the way from the left all the way to the right, is it going to cross this y-axis at some point? Yeah. You bet. And only once is what you have to take on faith for, well, pretty much forever until you take pre-cal. Okay? It will, at some point, as it's doing whatever it does, it will cross that y-axis once. Okay? And only once. So there will be a y-intercept. There is not necessarily x-intercepts. Okay, so let's try x-intercept. Same idea, but we're looking at the x-axis now, right? Where does this line cross the x-axis? Negative 3, is that okay? It's okay? Does this quadratic, does this parabola cross the x-axis? How many times? So we have 2. That's why they put the little s in brackets. Right? It's x-intercept or x-intercepts if there's more than one. Right? So? No, you want both. You want both. So 0 doesn't matter. As long as you list them both. I always, you will notice when I'm listing, will list from left to right. Because that's an ingrained habit, right? But As long as you got them, I don't care. Okay. How about that cubic? Is it crossing the x-axis? 3 times. So, -2, 1, and 4. Okay. What was the degree of the linear? 1. How many x-intercepts did it have? 1. What was the degree of the quadratic? How many x-intercepts did it have? And what was the degree of the cubic? Okay. There's a rule hiding in there, but you have to be careful. It's not guaranteed. A graph of a polynomial function will have no more x-intercepts than its degree. It will have maximum, whatever its degree is, number of x-intercepts. It could have less. Let me show you a parabola. Let me just grab a scrap piece of paper. Let me show you a parabola with no x-intercepts. A little sloppy. Does that cross the x-axis? With that shape, is it possible to have one x-intercept? That was a trick question. With this shape, can I move it around somehow so that it has one x-intercept? If I just tap it, no x-intercepts, one x-intercept, and two x-intercepts. Is there any way this shape is going to cross that x-axis more than 2 times? No matter how you move it or flip it or turn it around, it's going to cross at most twice. It could cross no times, 1 time, or 2 times. Okay? For a cubic, same thing, except there is no way that a cubic will not cross the x-axis at least once, and we got to get into end behavior to talk about why that is. Okay? Same thing with a linear. If it's a linear, it's going to cross the x-axis once, unless it's this stupid thing. Okay? We're not talking about this stupid thing anymore, right? So when I say linear, you know I mean like a slanty line. Okay? This will cross once, always once. There will be an x-intercept always. Okay? This could be no x-intercepts, 1 x-intercept, or 2 x-intercepts. This could be 1 x-intercept. Okay, let's do this in pictures. 1 x-intercept. There's a cubic with 1 x-intercept. Could be 2 x-intercepts. Right, here and here. And 3 x-intercepts. Okay, can't be 0. I'll get into why in a minute. Now when I say those things, a lot of people go, okay, I'm going to memorize all that. That's the worst way to learn anything, right? Because if you memorize something, you're going to forget it like that. And especially if you're in applied math, to go somewhere else and do something with it, whether that be nursing or engineering thing at Red River or whatever it is, you're going to memorize some crap, and you might make it through the exam, but you won't make it through the summer and then starting your course. That stuff you memorized will be, right, better that you understand it. So when I'm talking to you and I'm saying could have 1, 2, or 3, you don't have to go and memorize those facts. It's just more for interest's sake, right, to deepen our understanding. Okay, this end behavior business. Now you're absolutely right on the quadrants. I want to make sure everybody knows what the word quadrant means and how quadrants are labeled in math. When you make an x and a y axis, you split a 2-dimensional plane, which is just a fancy way of saying an infinitely thin, infinitely big piece of paper. Okay, can you imagine that? It's got no thickness, which is impossible to imagine, but you have just, think of a wall that you can paint on the outside of, infinitely big. Okay? On that infinitely big thing, you find the middle. Okay? Can you find the middle of something that's infinitely big?
I don't know.
For something to have a middle, it has to have ends. Right? Where's the middle of this pen? Well, I don't know. It's out there. How do I know? Because it's the same distance from either end. Without an end, there's no middle. But a lot of people call that origin the middle. It's not, it's just a randomly located thing that happens to be labeled 0, 0. Whatever, but I'm going to use middle, okay? So right in the middle, you put a point, you call that 0, 0. You put an infinitely long x-axis and an infinitely long y-axis crossing through 0, 0. Horizontal and vertical. You with me? It's really big. As soon as you do that, you split that two-dimensional plane up into 4 sections. Right? And I'm pointing at these in order for a reason. This section, this section, this section, and that section. They are called quadrants. The quad part meaning 4. Okay, you split it up into 4 quadrants. The 4 quadrants are numbered. And this isn't Gord's numbering, this is math numbering. Okay, and it's normally written, again, if you're like me and severely anal retentive, you put a big Q and you put a little Roman numeral with the number of the quadrant. So this quadrant is quadrant 1. Why did they pick this one to be quadrant 1? Because it's where the X is positive and the Y is positive. A lot of science, especially when we go hundreds of years ago, happened in the first quadrant, right? When they were trying to develop scientific rules and stuff, all the graphing was up here. They didn't worry about what negative things were. Okay, so this gets quadrant 1 because everything's positive. Okay, and then they could either start going this way and say this is 2, or this way and say this is 2. I don't know why they picked the way they did, but they go counterclockwise. Right? So if this one's 1, this one is 2, this one is 3, and this one is 4. If you're sitting right on an axis, if you ever want to have some fun, find 2 mathematicians, ask them whether this point here is in both quadrants or neither quadrant, and just sit back.
And then just walk away or
Well, yeah, you can walk away because eventually it will get very boring. But I've actually seen math professors yelling at one another over whether that point is in both quadrants, 1 and 4, or neither one. Right? Imagine you have 2 farmers' fields and they're a fence, and you're just as skinny as the fence, just like me. It's a big fence, okay? And you're sitting there on the fence. Whose farmer's field are you in? Both? Neither? What's that? Who paid you? That's a good question. A good question. The answer is there is no answer. That's why math people argue about it all the time. You can't look in a textbook and see this is in both quadrants, because there isn't really an answer for that. It's not going to matter to us anyway. I'm not going to give you a point here and say, hey, what quadrant is that in? And sit there giggling to myself. Okay? So quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay? When they say end behavior, what they want to know is in what quadrant is the function coming from, and to what function is the quadrant going to, or where does the function originate and where does the function terminate. Okay? You need to know these. Now if you think you might forget them, right on the top of your cheat sheet you could write a little cross and put Q1, 2, 3, 4 like that. Right? I don't care if they're Roman numeral. If I say where do they begin and end, and you say quadrant 2 to quadrant 4, fine. But just know that formally they're written as Roman numerals. Okay, we're gonna do it now. Okay, so yeah, that was a very quick blip. Here we go with a bit of more detail. Okay, so I want to know. Let's look at the line. Okay, always remember left to right. Although I will also tell you I won't freak out if you get this backwards. Okay, so starting on the left, and I don't mean this left. I mean that left. All the way left. Okay? If I go all the way left, if I go all the way left, in what quadrant is my graph located? ever gonna exit quadrant 3?
No.
No. Okay, so now we're supposed to be going left to right, so I'm starting in quadrant 3, if I'm looking at this graph, and as I travel along the graph, I pass through quadrant, I'm not quite tall enough. There, a little fun story here. It was my first year teaching at St. John's High School, my third year of teaching overall. And one of my students had fallen asleep at their desk, which, as I know now after 20 years, man, I'm boring. But at the time I was all indignant, young teacher, whatever, so I got my meter stick out, and I just kind of wandered over to his desk, and I went, I'm not going to do it because it makes a really loud noise, but it's really got on the desk. You can imagine how loud that is. You start from here, it goes crack, right? And he goes, and he kind of does whatever, and then he pees his pants, and I'm like, oh my God, I'm so fired. I just figured I was done. I was packing my stuff into the thing or whatever. And the funny part of that story is, years later, I see him at St. Patel Center, and he comes over, Gord! And I was like trying to do one of these, right? Gord! And he goes, oh, hey, how are you? I don't remember anybody's name. If you've seen me in 15 years, I'm not going to remember your name, I'm sorry. So you just go, I'm so-and-so. I do remember I taught people. I can remember faces, right? So I'll know that I taught you, I just won't remember when or where it's made it. Okay? So he comes, hey, how are you? I'm like, good. And I remembered him. I didn't remember his name, but I knew he said, hey, how are you? And I'm like, good. Hey, you remember that time I did myself in your class? And I'm like, yeah. He's like, oh, it was awesome. And I'm like, oh.
Did you feel bad?
I felt really bad. I didn't mean for that to happen. I was just trying to like have a little funny, right? I didn't mean to like, and he wasn't scarred for life. He thought it was funny, so. I don't do that anymore. I learned my lesson, okay, once, but I didn't learn it. Okay, so back off of P, sorry about that. So we're coming from quadrant 3, we're going doo-doo-doo-doo-doo-doo. You do have to sing like that as you go over the graph, doo-doo-doo-doo. We go through quadrant 2, right, look how nice quadrant 2 is. You can look out the windows. I took that train that goes from London to Paris this summer. It travels at about 300 kilometers an hour. So I went through quadrant 2, whoosh, oh yeah, there it goes. Where do I end up? If I keep going, is this graph ever going out of quadrant 1?
No.
It is originating in quadrant 3. That's the fancier word. It is terminating in quadrant 1. Now both of those words are wrong. And because I am anal retentive, I have to correct myself. Originate means what? To come from, or to begin, or to start. Where's the start of this line? There is not one. It is infinitely long. I said it terminates. What does terminate mean? It's what they should have done to me in my third year of teaching. To end, right? Does it end? No, but we use those words anyway. Those words are in common practice. We say it originates in quadrant 3 and in quadrant 1. Is that one making sense? Okay, I'm going to make it worse. You would write when they ask you for end behavior is quadrant 3. You can write out the word quadrant if you really want to. I'm way too lazy. Quadrant 3 to quadrant 1. Now I'm going to tell you a couple little secrets. You're not going to tell anybody I told you. I already told you this one. If you make that a normal 3 and a normal 1, no problem. If you reverse those, even though it's not left to right, it's fine. It's not as formal as the domain, the interval notation. That must be low end to high end. I will correct you. Like if on a test you wrote quadrant 1 to quadrant 3, you'll see red pen. I'll put little arrows saying move them around. But it's not, you're still okay, right? If you just said 3 to 1, that's okay too. They accept that on the exam. But I don't just want to teach towards the exam. I don't know where you're going. In my 16 years in this building, I've had lots of students start at essential math, go to grade 12, go, I kind of like that. Go to applied, go to grade 12, go, I'm really liking this. Go all the way back to grade 10 pre-cal and pre-cal it out. Okay? Hi Kim, this is Kim.
Hi.
A good teacher, if you're wondering,
Hi,
just for comparison. Right? If you said 1 to 3, it'd be okay. Okay? But generally you want to talk left to right. Okay? And that's what I'm saying. If you're going ever to university to take math, they're going to want you to talk left to right. If you said 1 to 3, it's okay. But it'd be okay. I would mark you right. Final exam, it's right. But I'm not just teaching for the final exam. Okay? It's okay. It's not right, but I'm not going to mark you wrong. Okay? Does that make sense? Left to right. Just think left to right. What's on the left of quadrant 3 and 1? 3. What's on the right? 1. 3 to 1. Try to do it that way. Okay? I'm just saying don't lose sleep over it because it's going to be okay. Okay, look at this quadratic. In what quadrant is that quadratic originating? 2. So as I go this way, I know I'm supposed to be going left to right, but bear with me. If I kept going that way, is it ever going to go out of quadrant 2? Is it ever going to curve back and come back over the y-axis? No. Is it ever going to curve like this? No. It's going to keep going up like that. It's going to keep getting steeper and steeper and steeper, but it's going to keep continuing to widen out. Look, I'm multimedia right now. Okay? So it starts in quadrant 2, goes woo, kind of dabbles around in quadrant 4 there, bends up, and where does it end up? 1. So the end behavior of that quadratic is quadrant 2, 2, quadrant 1. We're going to do the cubic, then I'm going to try to make things harder. Yes, yeah. As long as it's understandable, I find. This isn't, like domain and range are fairly formal. This isn't. So just as long as it's understandable, it's okay. Okay. Okay, let's look at this cubic. Left to right. I mean this absolutely not as a joke. If you're not sure about left to right, you know the good old trick, right?
Yeah.
Which one of these is an L? Left. Okay, left to right. Okay. What quadrant is this starting in? 2. And then has a little look at 3. Has a nice dabble through 4. Swings around 1 for kick. And then goes out which one? 4. So this is quadrant 2, 2, quadrant 4. Excuse me. I'll come back to domain and range. I need to find some paper. You can write these down if you want. I'm not intending for you to write these down. I'd just rather you just watch and play along. Okay? I'm going to try to give you a couple of questions that people will get incorrect. Okay? Classics. Here it is. I'm going to do the graph in red pen just to make it stand out from the axes. This is a classic exam multiple choice question. Question would be, what is the end behavior of this function and then they would give you 4 choices, quadrant this to this, quadrant that to that, and there'd be 4 choices there. Okay? After every provincial exam, they send every school's principal a report of how the school did and how the students in the school did, but also provincially how students did, and then a breakdown question by question of what questions people got right, what they got wrong, how many marks they got on each question. This question, and ones like it, is commonly answered correct by about 20 to 30% of the province. That's why we're looking at it specifically. What is the end behavior of this graph? Let's start at the left. What quadrant am I in? 3. Right? I come up. What quadrant do I end up in?
4.
3.
You're always widening it up, so it'll end up going across.
I could have paid you money for that one. You should have demanded the money first. Okay? You're always widening in a parabola. So when you look at this, what quadrant is this little arrowhead in? 3. But as the graph continues, is it going to go over the y-axis? Absolutely. That graph continues to widen forever. It gets wider and wider and wider. So if I kept going, I don't know if I have enough paper or enough artistic skill. Eventually, it's going to cross that y-axis. So the initial quadrant is quadrant 3, but it ends up in quadrant 4. That's weird, right? There's a reason that only 20 to 30% of students get that right. Because it's weird. You look at it quick, you go, oh, 3 to 3. I will tell you this. Any function that we look at, I don't care if it's linear, quadratic, cubic, exponential, logarithmic, or sinusoidal. Those are all the ones we're going to look at. None of them originate and terminate in the same quadrant. So if you're trying to say from quadrant 3 to quadrant 3, I guarantee it's wrong. Okay, does that make sense? Okay, let's try another one. Very similar question, but I'm going to use a cubic.
What answer is this one?
So this one is quadrant 3 to quadrant 4.
We can check it right on the calculator to find the y-axis.
Yep.
Right away, but
Yep.
yeah.
If you know the equation,
Yeah.
right?
The one you're checking.
That's the kicker. But if they just draw you the graph,
Yeah.
then you're in this situation, right? And they will do that. But yes, if you know the equation, you could put it in your calculator, you could start zooming out, right? And then you'd actually see it cross the y-axis eventually, right? Okay, let's try this with a cubic. Quadrant 2 to quadrant 4. Quadrant 4 is okay, right? You see it going out quadrant 4? It's not going to do anything, it's going out quadrant 4. Is everybody okay with the quadrant 2? This part in quadrant 1, but all you're seeing here is an infinitely small piece of an infinitely large graph, right? This will keep going and widening and widening and widening till it crosses the y-axis and goes into quadrant 4.
This is mine, or like the other one, like.
Yes, always. So when you're going, where does it start? And that's why, remember with the line, when I was looking at the line, I didn't kind of point it where the end was, I kept going. That's what you gotta think. When I'm infinitely way that way, what quadrant
So
is
it
the
wouldn't
graph?
be quadrant 1, it would be quadrant 2 then.
Right, quadrant 2 to quadrant 4. The popular wrong answer would be quadrant 1 to quadrant 4, because you just look at this and you go, oh, that's in quadrant 1, and you stop looking. So you gotta be a little bit careful there. Now, they're not gonna throw that at you all the time, right? But that is something to watch out for. So this is quadrant 2 to quadrant 4. Okay. And there's a whole thing with x-intercepts in there, but I don't know if I want to get into it right now. Might play with it later when we have some technology. Okay, are you okay with what I'm saying here? Is this making sense? If for this one you said 3 to 3, don't feel bad. That is a very common answer, right? And that makes sense, right? When I said, what's the end behavior? Nobody said, egg, cloud, right? We're on the right track, right? But it's a little glitch you gotta watch out for. Okay, domain and range. I'm gonna cheat. You ready? Are these all polynomial functions?
Yes.
Okay. What are their domains? I'm not even gonna look at them again. I'm just going to do them in interval notation. Again, you're more than welcome to do them in set notation.
You would always have the choice.
Yep, whatever you like.
They won't say, you won't say you have to do a set.
Nope, nope. The only reason we look at both is because I don't know what resources you may use throughout the year. Like you might go on the internet, right, and look up domain or whatever. And some places will have set notation, and some will have interval notation. Right, so I show both so that when I'm using, like actually me myself want to write domain or range, I use interval notation always. That's just me. This, yes, for all polynomial functions, from negative infinity to positive infinity. Okay, what's that? For all polynomials, so for all linear, quadratic, and cubic functions, same domain. They all go left forever and right forever. Okay. The range for a linear and a cubic is the same. Nope, none. The cubic will always be one of two general shapes. Okay. And there's a whole bunch of pre-calculus proof in here. It'll come from the top, and it might do something wonky in the center, and then it'll go shooting out. A cubic is overall always decreasing or increasing. In the middle it might change, but I start decreasing and I end decreasing. So because of that, the range is always going to be up forever and down forever. It might be turned around, it might look like this,
If it doesn't have
right? But down forever and up forever.
If it doesn't have arrows,
For now, don't worry about if it doesn't have arrows. They all will for now. Okay. We will look at what you have to do later is in specific applications you have to assume there's no arrow. Right? Like if you're timing a bird in flight and you're starting timing at 0, there's no arrow on the graph past that. Okay. So up till now, the only thing you have to watch out for domain and range wise is the parabola. Oh, sorry. For the quadratic? The domain? This? Are you talking about that? Well, you could do that there too. I'm just saying you could write either one. Right? Is that what you're talking about? Yeah. Don't write both. Okay? Just get out of that habit. Pick one, pick the other, go for it. Okay? I mean, and when I said don't write both, I mean don't write both as one answer for the same question. If you want to do a question and have your domain in interval notation and put the range in set notation, no problem. But don't do both for the same one. The reason I say that is holy brain fart. It's for your exam. If you give me both and one of the two of them is incorrect, the whole thing is incorrect. So pick the one you're more comfortable with and just put that down. Okay? Also, like for fractions, do you ever have a math teacher that insisted that you reduce your fractions? stop. Okay? And I don't care if you're going to pre-cal. Stop reducing fractions. You know who had to reduce fractions? People who did not have access to calculators and computers. So when I was in high school, and this is no word of a lie, 92-year-old math teacher told me to reduce my fractions, it's because when he was in high school, it's easier to work with a reduced fraction because the calculations involve smaller numbers, and when you don't have a calculator, that's nice. Right? Not anymore. Doesn't matter.
Everything is by hand for all the tests. You have to get 95% and it's all fractions.
Yes. Don't worry about it. You'll learn it when you get there.
Well, I already
It's all proportions, right? It's all,
Ratio.
yeah, because you have to get the right amount of medication or whatever, and
Yeah.
yeah. Okay, so for range, for the quadratic, let's look at this sucker. I'm going to do this first in interval notation. How low does this go? -4. Okay, if you give +4, I'm going to mark you wrong. Just fair warning, that's -4. Would that get a round bracket or a square bracket? Square, because it does get all the way down to -4. Boop. Okay, and then how high does it go? Infinity. So the high end is infinity, and that gets a round bracket. Infinity always gets a round bracket because you can't get to infinity. Right? You just can't get there. Okay, let's do these ones quick, and then I'm going to take a math timeout. We're going to do attendance, and I'm going to start assigning graphing calculators at the same time. Okay, and then if we'll have time, we'll start looking into lesson 2 there a little bit. Okay, so it says reflect on your responses in the table in 1 to answer the following questions. In a perfect world, I'd send you home with this and you could think through it and try it out. I'm too busy. Let's keep going. How is the possible number of x-intercepts related to the degree of a polynomial function? We talked about that, right? A cubic function can have at most 3 intercepts. Same as the degree, right? So I'll put max x-intercepts same as degree of function. I hate writing. I wish I could type everything. If you can't read what I've written, you're not the first, you won't be the last. Just tell me and I'll try to write it more neatly. When I student taught 400 years ago, my cooperating teacher said, "You're a good teacher, explain things well, everything looks good, but your handwriting's terrible, you've got to work on it." I said, "Okay, I'll do that." They keep paying me. That's okay. Got to be good enough. Okay. Does every quadratic function have 2 x-intercepts? No. I showed you some that don't. For example, this dude has none. Okay, so no. What's that? Linear ones will have 1 x-intercept, always. Okay. All polynomial functions of degree 1, 2, or 3 have only 1 y-intercept. Do you agree or disagree? Explain. That's not really a fair question for the level of math that we're in right now. That is a pre-cal 40 question at the end of pre-cal 40. Okay? You kind of know this. All of these polynomial functions have a domain of negative infinity to positive infinity. We talked about this. So as you're traveling from the left to the right, at some point you're going to cross the y-axis. Right? Do you agree with me there? What I haven't explained to you, and I'm not going to get into, is how you know it only crosses once. Okay? This even though it's kind of cubic looking, is not a function. Okay, I'm going to give you the quick explanation with my terrible Coke machine example, and then we're just all going to agree to move on. Ready? The x-axis is the button you press on the Coke machine, right? So if I press the Coke button, what should I get? A Coke. The y-axis is my output. What this graph is doing is saying if I press the Coke button, I could get Coke, or I could get Sprite, or I could get root beer. For that one x value, 0, for example, there are 3 different y values. That's not a mathematical function. The definition of a function, which I'm not writing down, and I don't want you to write down, and you don't even need to know, but the definition of a function is for every single input value, there is a maximum of 1 output value. The Coke machine example actually works, because when you press Coke, you could get a Coke, that's 1 output value, or you could press it and it's sold out and nothing happens. So that's not a, there's no, right? So maximum of 1 output value, okay? Anyways, if you're looking at that going, wow, that's the most amazing thing I've ever heard, we've got courses for you, okay? So yes, let's just go with that. Polynomial functions will have 1 y-intercept. Take my word for it. Polynomial functions all have 1 y-intercept. Even that dumb horizontal line. Okay? Describe how the end behavior of a polynomial function is related to the degree of the function. Oh, I'm sorry, I've got 2 questions. I'm not even looking.
For question B.
Yeah.
I did write.
Oh, sorry, I would write no. And then, you know what? I wouldn't write anything. I would do this. That doesn't have 2 x-intercepts. That doesn't have 2 x-intercepts, right? Picture's worth 1,000 words. Same question? Okay, sorry about that. Yeah, I kind of skipped over fast. For people who have not yet asked a question, you will notice the people who have asked a question are still breathing and alive, correct? And I haven't yelled at them once. So if you have a question, don't be shy, right? They pay me to answer questions. That's what I'm here for, okay? Although I'll tell you this, I'm not writing down the answer to D because it's too long and I'm too lazy. Okay? I'm going to get up and wave my arms around. Okay? Tell me how the degree, what does it say? How the end behavior of a function is related to the degree of that polynomial function. Okay? Start with linear. What is linear? That was a stupid question. There's about 40,000 answers to that question. Let me rephrase that. What does the graph of a linear polynomial function look like? Not necessarily. It could go up by 1/2, go down by 7. Even simpler. If it's linear, what does it look like? It's a line. The graph is a line. Okay? Not this. That's supposed to be vertical. I realize there's a bit of it. Not this. Not this. But anything else. Right? Linear. Okay? All polynomial functions of degree 1, linear, will go either from 3 to 1 or, I'm going to do it left to right, 2 to 4. Okay, that's it. You can't have a linear function going from 2 to 1 because the line has to turn, right? 2, this is harder to do than it looks. 2 to 4, 3 to 1. I'm going to skip over to a cubic.
Can I spell a photo for that question?
Absolutely. You know what, I'll do that too. I'll come back and I'll put pictures, okay? But I like to do this for a while, stretching. Okay, let's go to the cubic. Okay, what is the degree of a cubic function? 3. Okay, now this is a bit of an open-ended question. What's similar about the number 1 and about the number 3? They're odd. They're both odd. Every cubic function will start in 3 and end in 1, just like a linear, maybe with some woo-de-woo in the middle, but it will go 3 to 1, or it will go 2 to 4, just like a straight line. Okay, so I'm going to write here odd degree functions either that's supposed to be a question mark in the middle. 3 to 1 or 2 to 4. Hello. Hey, what's up? Are you in here?
Yeah.
Yeah? You in here? Yep, right. Okay, let me have a seat. No. Okay, that applies for all polynomial functions. If you had a polynomial function of degree 9, it could start down here. If it does, it'll come up. It could do some really wonky stuff, but it'll end up going out that way. Okay, if it's an odd degree, it's going to go 3 to 1 or 2 to 4. So I say, if you can think of that for a straight line, any odd degree function is going to do the same thing, either this or this. Okay. What if the function is of even degree? Everybody knows odd and even, right? Okay. You can ask any questions. If I'm talking and I don't make sense, you let me know. Try not to assume. Okay, so even numbers are numbers that you can divide by 2 evenly, split into 2 groups evenly. So 0, 2, 4, 6, or 8, or any number that ends in 0, 2, 4, 6, or 8. And then 1, 3, 5, 7, 9, or any number that ends in 1, 3, 5, 7, 9 are all odd. If it's a decimal number, it's not even or odd. It's a decimal. Okay? Okay, even degree. We've only looked at one type of even degree polynomial function. That's the quadratic. It looks like a parabola. That is degree 2. It's either going to go from 2 to 1. Need a longer shirt. I'll do this. Okay. Or 3 to 4. Okay. Any even degree polynomial function, and we don't look at any others, because you don't have to worry about this. But if it's degree 18, so you have an x to the 18th as your highest exponent, it will maybe come from 2 and go to 1. The middle might be real wacky. Okay, but at the end, it's going to go from here to here or from there to there. Okay. That's even degree. So if I'm doing pictures, I'm just going to draw parabolas because that's all we care about, right? So 2 to 1 or 3 to 4. And of course, I'm not even following my little rule in here, right? I'm not writing Q3 just to save space. May I speak bluntly? Sure. Okay. I think question E is stupid. If I saw that on the exam, I would drive down to the Department of Education and complain. And I've actually done that. Good times. Okay? What? I'm gonna answer it. You'll notice I'm not gonna write it down. You're not gonna worry about it. You're not gonna go home and study it and try to make sure you know the answer to this question because it's a stupid question. Okay? I will say this, the domain of every polynomial function is the same. Domain. Negative infinity to positive infinity. Right? I don't care what the degree is. If it's a polynomial function, it has the same domain as every other polynomial function. Okay? Easy. The range, I would be okay with this question if they left out domain, because the range, there is some difference. I'm going to go odd degree, even degree again. Odd degree polynomial functions, because they either do this or this, have a range of negative infinity to positive infinity.
So I just wanted to say that if it is a polynomial, the domain is
Unlimited, if you want to put a word in there. Okay, that's correct. If it's an odd degree, its range is also unlimited. Right? It goes down forever and up forever, whether it's going this way or this way. Right? If it's even degree, okay, the range will have a boundary point somewhere. Okay? It might be bigger than whatever the boundary point is, or it might be less than, but there's a boundary point. Okay? It's tied in with the end behavior, right? So the only thing at this point that you really have to be careful about when I ask you about domain and range is the range of a quadratic function, the range of a parabola, because that's the only one that's different, right? That you gotta watch out for. And because it's the only one that's different, what's the chance I'm gonna ask about that on the test?
very good.
Very good. Because otherwise, what am I testing? That you can copy something down? You can already do that. Right? I need to test this. Okay? Explain why cubic polynomial functions have turning points but not maximum or minimum values. Well, I was going to jump back, so this is as good a time as any. We won't get to lesson 2 today. We skipped 2 things in here. Minimum values and maximum values. Okay? It's not on that chart that we did. Okay? I'm writing a note to myself because I'm going to be fixing this book at some point. We write these booklets here in-house. They're always trying to be improved. Sometimes we try to improve them and we make them worse. Okay? Let's go back to these graphs. Okay? I want to do the maximum and minimum values, if applicable, for each of these 3 graphs. I don't want you to panic about this yet either, because this is something you'll be doing mostly on the graphing calculator. Okay? Look at this line. What does maximum mean? The highest, higher than anything else. What's the maximum number of people we can fit in this classroom? I don't know the answer, but let's, like 200? If everybody was like, just standing there? I don't know. Okay, but there's a maximum. Would you agree? There would be a point where we couldn't cram even one more person in the door. Even if everybody laid down and we stacked everybody up to the ceiling, at some point you'd fill up the room, right? Okay. What's the minimum number of students we could have in here? 0. Because negative doesn't make sense in that context, right? Maximum is the biggest number. Minimum is the smallest possible number. Note the possible. Look at this line. Now when I say maximum and minimum, I mean maximum and minimum y value. Always means y value, always.
And more.
What's that?
So you meant on the line.
Like when you're looking at the line and you're looking at all the y values it passes through, okay, what is the maximum y value for this line?
4.
Does it go higher than 4?
Well, it touches leaves the line at 6.
It goes higher than 4. Does it go higher than 6? Okay. How high does it go? Forever. So what's its maximum value? Okay. If you answered infinity, good answer. Incorrect. That was a mean, bad trick to play on you, but it's incorrect. A maximum value can't be infinity because infinity is not a value, it is a concept. Okay? Just like cow. Fill in any noun that you want there. Just like building or street or shoe or video game. Right? It's a word that means something, it's not a number. Okay? So let me ask you again, and this is just me being mean, what is the maximum value here? No? It goes way past 6. Look at it. Look at it go. There it goes. Holy crap. Look. Man. It does not have a maximum. There is no highest value, because when you think you're at the highest value, it keeps going. Right? How many students can we fit in the universe? Depending on your particular set of beliefs, that answer could be there is no maximum. Keep packing them in there. Right? What's the minimum value? It goes lower than 0. Okay. And the same thing with negative infinity. There's no maximum, there's no minimum. Okay? Let's flip to the cubic. That's for linear. And that's in gen. No maximum, except for this dumb one. The horizontal one, its max and min are the same. It's whatever number it passes through. Don't worry about it. Okay? The cubic. Okay? Careful, because I'm playing the trick again. What's the maximum here? 4? Does it go higher than 4? Yeah, look at it. There is not one. It goes up. I know it goes up, and then it kind of goes down a little, and then it keeps going up. But we're looking for the biggest Y value it gets to. And it keeps going and going and going. It doesn't get to a biggest Y value. It just keeps going. No maximum, even though there's this little hump here. And you won't need to know this for applied, but they call that little hump a local maximum. Meaning if you just look at that little section of the graph, it's a maximum there, but don't worry about it. Okay. No max, and guess what? No min. Because it goes down, it keeps going down forever. Okay? So why am I even talking about this? This one. What's the maximum value? I mean, if you say infinity, I get what you're saying. But the formally correct answer is there is no maximum. Okay? Does this have a minimum value? Does this graph get to a lowest point? Right there. Does it go any lower than that ever? No, that is the absolute lowest it gets to. So what's the minimum value on this graph? -4. If I turn it around, I don't even know what time we're supposed to stop in here with this slot and a half.
1:30.
Is it? Okay. Something like that. I guarantee every day I'll try to go somewhere between 1:15 and 1:30. Okay. If you're new, because I haven't been telling everybody as they come in, this is a slot and a half. They have not been good about putting that on the schedules. So it's not 2 slots like some people's schedules show. It's a slot and a half. I think 1:30 is the cutoff time. As long as one of you wants to stay, and this will start to apply when you're using the graphing calculators, because you can't take those home with you, not these ones. Okay. So if you're in here and you're working and you want to just keep working for a bit and 1:30 comes, I'm not going anywhere. Okay. I told somebody the other day, I don't remember who, that Raven, right? I told you that I didn't know what class was in here after. Yes, I do. I'm an idiot because it was my class that was canceled because it had no people in it. So there's no one in here. I got nowhere to go till 3:15 most days, so I can just sit in here. If you want to sit there working on a graphing calculator, I can just sit in here, whatever, right? So, but 1:30 is the formal time. Okay, anyways, blah, blah, blah. A little downward facing parabola. Let's do this one. And let's say that's at 3. Can you even see that? No, there, this. Does this have a minimum? Goes down forever. Does it have a maximum?
Yes.
At 3. Okay. Again, I'm not worried about adding that to the chart because you'll look at that more with the graphing calculator. Okay. So here's what I'm going to do. I'm going to take attendance. I'm going to try to remind myself what numbers they're using in here. And I'm going to assign you a graphing calculator. I'm not smart enough to open the door, but I can do math. Okay, I would like to talk seriously with you for a minute. Okay, is everybody paying attention? Okay. I want to be crystal clear. You listening? Everybody? Chaos, you listening? Listen. It's not math related. It's life related. I'm going to assign you a calculator number. You will start getting into the habit of when you come into class, you will grab your calculator out of that thing. You'll use it in class. And then it has to go back in there at the end of class because other classes need the calculators that are in there. Okay? If your calculator disappears, you will be held responsible. And the first result is you will not be lent another calculator. Okay? You can't complete this course without a graphing calculator. So at that point, and this has happened, you either have to go and spend $140 of your own to hopefully replace it, but I guess you could keep it too, or you have to find it, okay? If you walk out of class with it because you forgot and you put it in your bag, it's all ha-has and giggles the first time. But when you take a calculator out of there and put it in your bag and forget, because I have had students that forget because they really want to work on something at home, so they forgot and put the calculator in their bag and went home, you're depriving every other class of that calculator that uses it up till our class gets back in here again. It doesn't make me happy. Okay? Now we're all adult students, we're all responsible, right? I haven't had any problems with theft or anything like that, but I would also like to say that if you're calculator number 1 and you walk in here and calculator number 1 isn't in that slot, don't take a different one. Turn around and tell me immediately, because I will go to the teacher of the previous class and say number 1 is gone. You need to find that student and bring it back. At that point, I will give you a new one for that day, and then we'll find the old one. Okay? There are calculators you can sign out from the library. In order to do that, you need to see me first. I will sign this sheet that says that I approve of you taking a calculator from the library. Darcy, the librarian, will make sure not just that you have this form, but that you don't have any overdue books or any other kind of stuff from the library. If you have 19 overdue books and you go up to take a calculator, she's going to say tough. It doesn't matter how many of these sheets you have filled out. Okay? So it's a problem. They are $140 each. We cannot afford as a school to continue to replace entire class sets of calculators. We were barely able to afford the ones that we have now, and we're lucky that the superintendent let us have them. Okay? So, you know what, I changed my mind. I'm not going to bore you with the assign process today. I'm going to quickly take attendance, and then tonight I'm going to just work on giving you all a number, and when you come tomorrow I'm going to tell you what number you are, and you can take a calculator out of the drawer. Okay, does that all make sense? Okay, great. I don't anticipate any problems. Typically there are not any problems. If you don't bring the library calculator back, well, I know Darcy, and it won't go well for you. Okay. Now, where did I put my attendance? I'm about at my wit's end here, I swear to God. The homework is no homework again. Okay, we are going to start ramping up a bit though. Okay. Okay, again, apologies for not necessarily knowing your names. Manira, right there. And I'm going to try to look at everybody's face as I do this. I really start to get to know you once we do an assignment and I have to hand it back to you. That's when I can start really slapping some names in there. Sidra, that's Sidra. If I do look at you and say that's Sidra and you're not, I apologize. I know you are, but I could get it wrong. Solomon, Faith, I think I knew that one. Des is not here. Chaos is right back there, right? Cool. Crap. Oh, Mariel, right? I'll get there. Amon, right there. Amon, perfect. Amon and Fiore. Am I saying it right? Good enough. Zanebe, I know. Ariam, that's Ariam. I know. Michael is not here, I don't think. Lucy's here. John. Okay. Andrea. Sanissa's here. Melanie, perfect. Melanie. And Zhang, it's not pronounced Zhang, but it's you, I know that much. I'm going to work on that. You're going to learn some math, I'm going to learn how to say your name. We'll both learn something. Dorothy. Joshua. Perfect. Joshua. Ace. Ahmed's right there. Sean. Right, Sean. Jomar. There, Jomar. I know this is painful for you guys. Mathos. Did I say it right? You just being nice to me? Okay. Maria. Yuri's there. Nahan, perfect, thank you. Nahan. Shawanish is right in front of me. Zaram, you can. Billy? Nope. Kiana's here. Fayla's here. Good. Dan? I'm going to say it wrong, but Mamanon, right? But that's you, right? I want to make sure. That's Daniel. I just want to make sure I got the right Daniel going on here. And Raven. Okay, thank you. See you all tomorrow.